Hello. In this lab, I tracked the motion of a 0.758 kilogram cart before and after it collided inelastically with another cart of mass 0.254 that is initially at rest. I observed the conservation of momentum in a perfectly inelastic collision. A perfectly inelastic collision, by definition, means that two objects collide and stick to each other. In such a collision, momentum is conserved. My results show that momentum is indeed conserved because after the collision, the added momentum of the carts was very close to the momentum of the initial blue cart. Let's start by understanding conservation of momentum. Momentum is equal to the mass times velocity. By choosing both carts as our system, we must add their momentums to find the total momentum of the system. Thus, m1v1 initial plus m2v2 initial represents the total momentum before the collision. Since the red cart starts at rest, m2v2 initial equals 0. After this inelastic collision, the masses combine and move together at the same speed. Thus, m1 plus m2 times v final will be equal to our initial quantity as momentum is conserved in inelastic collisions. We can plug in the masses to get 0.758 v1 initial equals 1.012 v final. Thus, the final velocity should equal about 3/4 of the initial velocity. Now, let's measure the velocities to determine if momentum is conserved. Using Tracker, I have observed the position of the blue cart over time. Let's watch the video. Using markers, I track the position, and we can use these position and time points to find the two average velocities, one before and one after the collision. To find the first average velocity, we use the points 0, 0 and 0.701, negative 0.464. The second number represents the velocity and the first number represents the time. The change in velocity divided by the time gives us v1 initial as negative 0.662 meters per second. To find the average final velocity, we use 2 points after the collision, such as 0.868, negative 0.561, and 1.134, negative 0.691. The average final velocity equals negative 0.489 meters per second. Now let's look at Newton's second law, which is crucial since we are also using our model to predict motion. It states that the net force equals the mass times acceleration. We can rearrange this equation to get the version we will use in our code. Vf equals Vi plus F net divided by the mass multiplied by the change in time. In order to analyze the velocity and predict further motion of the carts, I used a VPython model. The model uses two separate time loops, one for before the collision and one for after the collision. We enter our two average velocities and the cart masses over here. Force is set at 0 since no forces are acting on the cart in the x direction. We are disregarding friction due to the minimal friction design of the track and the short time period of our collision. Using Newton's second law, we can update velocity and position. Since the net force is equal to 0, the velocity remains relatively constant, and the position can be updated by adding the current position to the velocity times the time step. This is the distance the cart moved in the time step. Here we have the first while loop, and now we have the second while loop, which occurs after the collision using a new velocity. Let's run the program. As you can see, the cart slows down at negative 0.53 meters when it hits the other cart. This reduces the velocity and changes the slope of our graph. Now let's look at the position points we observed versus the Python model. As you can see, the model predicted the position very well. Near the end of our observations, the model over-predicted the velocity. This is most likely because we did not account for friction in our model while it was affecting our system. Over time, the friction showed a small difference in the final velocity. Is momentum conserved in our inelastic collision? The answer is yes. If we plug our values into the conservation of momentum equation, we can see that the final and initial momentums are very close to each other. Both equal around negative 0.5. What if the carts were the same mass? What would change? As we can see from our simplified equation, after accounting for the red cart being at rest, m1 times v1 initial equals m1 plus m2 times v final. This shows that if the carts were the same mass, the final velocity after the collision would be half the initial velocity of our blue cart. In conclusion, in this inelastic collision, momentum is conserved and the final velocity is about 3/4 the value of the blue cart's initial velocity. The computational model also does a good job of predicting the motion of our two-cart system.